So, we have seen that a constraint satisfaction problem is made up of three sets. One is a set of variables, a set of domains for each variable, and a set of constraints on some subsets of those variables essentially. The solution to a constraint satisfaction problem, as we will see, is an assignment to all the variables such that all the constraints are satisfied. So, if we had specified the solution, then there would be nothing left to do, but instead what we do is we describe the solution in parts in some sense. So, we saw that we can represent the n-queens problem as a set of binary constraints. So, binary constraint network essentially. All we are saying is that what are the allowed positions for, let us say, queen 5 and queen 6 or things like that essentially. We are not specifying the whole solution, only in parts we are saying that this constraint must be satisfied between these variables. So, this is a little bit like the story of 4 blindfolded men who were trying to figure out what they were touching, and somebody would touch the leg and say it is a trunk, and somebody would touch the tail or something and things like that, and they are trying to figure out what is the object that they are touching. And we saw that binary constraint network talks about such a this thing. Now, we also said that the constraint satisfaction problem expresses one or more solutions, but the thing is that they are implicit. We know that the 6 queen problem has a solution, but we do not know what that solution is. We only know that queen 1 and queen 2 can be placed in these possible combinations, queen 2 and queen 3 can be placed in these possible combinations. There is a solution, but that is implicit, and that is what we need to kind of this thing extract from there. So, what is a solution? A solution is a relation on all the variables of the CSP essentially. Where is queen 1 placed, where is queen 2 placed, where is queen 3 placed, and so on and so forth essentially. So, we have seen this, that we could use a list representation for the n-queens problem, and so some permutation of A, B, C, D, E, F would be a candidate, and some of them would be solutions. And the relation is a relation on all the 6 variables, which means it is a subset of all combinations, all permutations of these. Some of them are the solutions. Solving the CSP is extracting a solution. That means, whatever was implicit in the CSP description, we want to make it explicit as to what are the 6 positions for the 6 queens essentially. And so, it is an assignment for every variable in the domain. So, there are 6 variables here, and we want values for all 6 of them. So, in some sense we start off with a fog of possibilities, and then when we solve it, we kind of clear the fog as to, okay, this is allowed and this is not allowed essentially. So, let us come back to the n-queens constraint network. That is, there are different ways that you could try to model these problems. And if you remember, the problem is that you have to place those 6 queens on the chessboard, which is of size 6 by 6, such that none of them attacks each other. One way would be that each of those 36 squares that you see on a 6 by 6 chessboard could be a variable, and all of them will have this domain that either there is a queen on that square or there is no queen on that square essentially, which we could also write as yes or no or 1 and 0 essentially. That is one way of trying to solve the problem. What would be the constraint? We could have one binary constraint which says that between any 2 variables, what is allowed? In square A1 if you place a queen, then in square A2 you cannot place a queen. So, this particular relation tells you what pairs are not allowed essentially. I mean, it says that in the sense where 2 queens cannot be placed. So, you can't place 2 queens on A1 and A2. You can't place 2 queens on A2 and A1 likewise essentially. So, and so on and so forth. That is one way of representing the problem. Another way that we have just seen is that we can have one dimension as the variable. So, earlier we said the rows are the variables, now we are using different notation where the columns are the variables. So, A, B, C, D, E, F are the variables and the values for each variable is this set of 6 values 1, 2, 3, 4, 5, 6, which means what, that queen on column A can be in row 1 or 2 or 3 or 4 or 5 or 6, and likewise for all the other queens which are on columns B, C, D, E, F. So, which is equivalent to the notation that we had seen a little while ago. The constraints are now on all pairs of variables which are columns. So, for example, where can you place 2 queens in the first 2 columns, and now we are talking about allowed rows essentially. So, we have said that for example, uh, in column 1 you can keep it on 1, and in column 3, in column B you can keep it on 3. So, that is allowed. So, if the first queen is here, the second queen can be here or here or here or here. In any of these 4 positions this can be done, and that is captured by this fact that this relation captures wherever the first value is 1, what is the second value allowed. Likewise, for if you place the first queen in row 2 or A queen in row 2, then the second one can be placed only in row 4 and so on. So, that is a binary constraint network that we have seen. If you look at the matching diagram for this, then let us try to get a feel of this matching diagram, and this should give us a feel of the fog of uncertainty that I was talking about. So, there are 3 things on this screen at this moment. On the rightmost is the chessboard on which you are trying to place the 6 queens. On the left side is the constraint graph. Remember, the constraint graph is a graph which tells you which variable is related to which variable. In our case, all queens are related to all other variables. So, it is a complete graph essentially. So, you can see that this is complete, which means there is an edge between any 2 variables. In the middle is what we have the matching diagram that we want to draw, and you can see that there are 6 clusters of values, one for each variable. So, each of them can take a value of 1 to 6. So, if you look at the relation between B and E, for example, then these are the allowed edges, that if you keep the queen in column B on row 1, then you can keep the queen in column E. So, remember this is B and E, this is not A, these are not contiguous columns. So, in general you can have a relation between any 2. We have been talking about relations between queen A and B, but now we are talking about queen B and E. And likewise, if you look at this carefully, you will see that for every location for column B, there are 4 edges going to the column E essentially. So, there are 4 positions where you can keep it essentially. So, this should, I hope this diagram is correct and there are no errors, but it should anyway give you a feel of what is happening. So, if you were to add 3 pairs, the opposing pairs in this matching diagram, then our set of edges in the matching diagram will grow essentially. And if we add more pairs, so for example, the figure on the right shows which variables we have considered, which is replicated in the yellow on the side. So, we have drawn the matching diagram for some of the variables, not all of them. So, for example, we have not drawn this one here, we have not drawn this one here. If we add that, then you can imagine that this would really become a fog of lines essentially. When you have stated the n queens problem as a binary constraint network, these are the possibilities that you look at essentially, and somehow you have to cut through this and arrive at a solution. Each edge suggests matching values for 2 variables, that we have already seen that. That is the whole idea of a matching diagram, and you can see that there is going to be a combinatorial explosion here, because all variables are connected to all other variables or related to all other variables. Once you clear the fog, this is what you are left with. So, this is a solution, it says that queen A should be in column 2 as you can see here, queen B should be in column 4 as you can see here, and so on and so forth. Queen C should be in column 6 as you can see here, and likewise for D, E, F essentially. So, this is what amounts to solving a CSP, that you now have a relation between these 6 queens. And what is the relation? If you were to express it as a tuple, it would be starting with A in that order. It says that 2, 4, 6, 1, 3, 5. So, as you can see, this is a permutation of the numbers 1, 2, 3, 4, 5, 6, and this particular permutation is a solution. It is a relation on those 6 variables. So, that is what R of A, B, C, D, E, F, and it is a subset of the different ways you can permute those 6 numbers, but this subset happens to be a solution. So, the next application we see of constraint satisfaction is comes from the domain of computer vision, and it is the task of interpreting line drawings. So, you assume that you have figures represented by line drawings, and you want to identify which of them are objects and which of them are not essentially. This work was done by 3 people sequentially, Guzman, Huffman and Waltz. Let us look at what Huffman worked on. He said that we are dealing with trihedral objects, only with trihedral objects, and there are no shadows, there are no cracks in these objects, these are solid objects. Each object is made up of 3 planes or 3 edges meeting at a vertex. So, each vertex in the object has exactly 3 things meeting there. So, for example, if you look at this vertex, it has 3 edges here. It also has 3 planes, of which you can see 2. So, this is one, this is another, and there is a hidden plane that you cannot see, which is the third. So, in a trihedral object, at every vertex there will 3 planes will meet or 3 edges will meet. Vertices are the junctions of these in these line drawings, and edges are the lines essentially. The figure on the right hand side is not a trihedral object, and the reason for that is that the top surface is not a plane. If you try to visualize this object, you can see that the top surface is not one plane, but on the other hand, if you had drawn a line somewhere here and this was a little bit different, then it would be a trihedral object, because as the figure is given to us, this is not a plane, there must be some curvature in this region, so that this part is ending lower than this part essentially. So, it is not a plane essentially. So, it is not a trihedral object, and one of the ways of identifying that is also the fact that at this vertex only 2 edges are meeting essentially. But in trihedral objects, at every vertex there must be 3 edges which come together. Now, essentially what is the task we are talking about? We are talking about the task that given a line drawing, to identify whether there are trihedral objects in that line drawing or not essentially. Now, Huffman showed that there are only 18 types of junctions. We will see that at a moment. So, junctions are vertices, we will see. He also assumed that there are no shadows, no cracks in the drawing, and that the objects are represented in what he called as a normal position, which means no exceptional viewpoints. So, an exceptional viewpoint, for example, is this one, where you can only see one face of the figure essentially. So, you can't figure out that the edges have 3 things meeting essentially, but whereas these 2 figures could be the same essentially, except that the viewpoint shows clearly that this is a trihedral object, the viewpoint on the right does not show that essentially. So, his goal was to check if a line drawing represented a valid trihedral object or not essentially, and there is a video you can look at on this by Patrick Henry Winston, who was their supervisor in MIT, and there is a link I have given here, or you can search for it on YouTube, interpreting line drawings essentially. So, there are 4 types of edges in such an object. One is labeled with an arrow. So, we are trying to label the edges in the line drawings in a consistent fashion. One of the labels that we will use is an arrow essentially. So, we have drawn it pictorially here, but we could use a symbol also to that essentially. What does it mean? It means that the material is on the right side of the object. So, for example, if this was an object like this, which is a trihedral object, assume that this is a cuboid and there is no, I mean these are all planes, but you can see that the material is on the right side of the object essentially, and that is what the direction of the arrow represents essentially. The other 2 type of objects are convex edges or concave edges. So, all the edges that we see in the diagram here are convex edges. So, the figure on the left gives you an example of these labeling. So, given the diagram on the left, the labels that we want to produce are shown on the diagram. What does convex mean? Basically, it is a convex edge where the material has an angle of 90 degrees essentially, or less, it could be less than 90 also. What is a concave edge? Where the material has an angle of more than 180 degrees. Material is all inside, right. So, the material part covers 180 degrees around that edge, or 180 or more, and so on. And arrows we have seen that this point, they show that the material is on the right hand side. Here is another diagram which is may have more than one interpretation and it is ambiguous, and these are the 2 interpretations. So, if you look at it carefully and try to understand what is happening, and the fact that these 3 edges are concave means that you are looking at a hollow part of a figure. So, if you were to look at, for example, the corner of a room, then that is how the 3 edges you see in the corner of a room on the top, on the roof, for example, they would all get a label of minus or negative, because these are concave edges. Whereas, the figure on the right, the same 3 edges in the same figure are labeled as positive essentially. What does that mean? That we are looking at a cube here essentially, and that is why they are convex edges essentially. This could have been a part of a larger figure which would look like this, if you can imagine it. Which would explain why these edges are positive, for example, essentially. So, anyway, the task is to label line drawings with these 4 kinds of edges, and the property we want to use is that there are only certain kinds of edges, vertices which are possible essentially. So, what are those vertices? So, for example, if it is a Y joint or a fork as shown here with 3 edges meeting and the shape looks like a Y or a fork, then these are the only possibilities. All 3 can be positive, all 3 can be negative, or one can be negative and the other 2 can be an arrow. These are the only possible in this thing. So, if you try to imagine any object where it has something different, for example, plus minus plus, you will not be able to imagine an object like that. So, in real objects, Y joints where 3 edges meet and they look like a Y have only these 3 possibilities. So, let us see if you can find a Y joint here. So, here there is a Y joint, you can see it has got 3 labels plus plus plus, and there is another one which is similar. Then there is another kind of vertex called a W joint. which looks like a W a little bit, and in physical objects they can only be plus minus plus, minus plus minus, or an arrow plus arrow. So, let us see, you can spot a W joint here, for example, it has minus plus minus, as you can see, or you can see a W joint here, it is an arrow plus arrow here essentially. This is also a W joint, and you can see that any type of trihedral objects, we are talking about trihedral objects, you try to construct a W joint will always have one of these two things.
Sir, one clarification. If we are talking about plus sign, it means that the part of the object is popping out, right? So just to
So, if you look at a cube, a simple cube, then all its labels will be labeled plus, except the ones where we can't see the material on the other side. If you can see material on both sides of the line, then it is a convex edge, and that is captured by a cube essentially. And a negative thing is like when you see at the corner of a room near the roof, there are three lines meeting there, and they will be labeled as minus, which means that it is a concave, three planes are creating a concave space in some sense, whereas on a cube you are making a convex space essentially. By convex we mean that the material is in the inside part of the thing, and by concave we mean that the material is on the outside part of this thing.
And what about the arrows?
Yeah, so let me draw a figure. We have drawn this figure earlier. Now, if you see this figure in isolation, the simplest way to imagine this is as a cube essentially, right, and that means what, you would label all the three edges inside as plus and all the other 6 edges with an arrow, because the material is like this, correct. So, but if you were to now imagine this in the context of a different figure which looks like this. Now, if you can imagine this as a solid object, okay. So, we are not talking about rooms and walls and things like that. This is a solid object which is got a hollow cube shape inside. So, it is as if you took this larger cube and scooped out one smaller cube from there. So, this would be negative, that is what we mean by concave essentially. On the other hand, this edge is positive, it is convex essentially. The material on the right side is kind of less than 90 degrees or 180 or less, whereas the material on both sides when it is negative covers angle of more than 180. I do not know whether that is the right way of describing it, but I hope you get the picture essentially. What do we mean by concave and what do we mean by convex essentially? If we had removed this surrounding figure, then all these will become convex, because now we are thinking of it as a cube, not as a hollow essentially. Okay. Then we can have T junctions. For example, here is a T junction. Let me remove the others. So, here is a T junction, and T junctions can be labeled in these 6 different ways. Either all 3 can be arrows, as in the figure that we have seen. The arrows can be in different directions, or sometimes you can have a plus or a minus in between essentially. So, you should try to visualize objects which have this kind of a 3 edges meeting at a T junction. And then there is the L junction where only 2 arrows meet in the line drawing. So, for example, here is an L junction, and L junctions can be labeled in these 6 possible ways essentially. So, we have 6 plus 6 plus 6 plus 3 essentially. So, here we have more than 18, but some textbooks will compress these into 1 essentially. So, some textbooks say that there are only 3 there, and but if you just think about it, you can see the point is that there are only certain combinations of labels allowed, and most books talk about 18 junctions essentially. Now, what is the constraint? How is it used here? It basically says that every edge is part of 2 vertices, and in both those vertices that same edge must be labeled in the same way. That is the basic constraint that we say that will be followed in the physical objects. So, here you can see that vertex 1 and vertex 3, they are essentially same kind of vertices, they are W vertices. So, not surprisingly they have the same kind of constraints, that plus minus plus or minus plus minus or arrow plus arrow, whereas vertex 2 is that y kind of a thing, and it has got these 6 things essentially. So, the only thing we are saying here is that if you are labeling this edge as plus in vertex 2, you must also label the same edge as plus in vertex 1. So, you must choose that combination which is consistent with this thing, and this you will see brings us to this idea of propagating these constraints to from one vertex to another. So, that eventually we will narrow down to the set of labels that we want to use. For every edge we want a label which is either plus or minus or arrow this way or arrow that way, and the task is to search for a consistent set of labels. Here is a simpler block. You can see that this thing which looks like a piece of cheese has got these 6 vertices, and there are some of them are W, some of them are L, some of them are one of them is Y, and 3 of them are W essentially. Which is the Y edge? The one that is in the center, which is V4. What are the L edges? V3 is an L edge and V2 is an L edge. So, this is V2 and this is V3, and the rest are W edges essentially. So, this one, and this one, 3 W edges, and these are the edges. We have given them names to the edges, and we also say that this is the first edge, this is the second edge, and this is the third edge. Now, if you look at this diagram, this basically is a constraint diagram. What are the constraints? The constraints are these kind of relations. What does this relation says? It says that the first edge in V5, what is the first edge in V5? It's that edge H is the same as the third edge in V6. What is V6? The third edge, it is also H. So, we are saying that it is the same edge, that every vertex has got 2 or 3 edges there, and this is the constraint, that if you look at vertex 5 and vertex 6, they share an edge, and that edge is identified by the index 1 and 3 respectively. So, the point is that they must be colored in the same way. So, if you are going to color this as plus, I am just saying an if here, you must also color this as plus. So, you must, if you are choosing this as a tuple, then you must choose the corresponding thing as a tuple where it has got the same label essentially. Sorry, I was talking of 1. So, 1 is this one plus, and that is the 3 of this one plus. So, this is the third one and this is the first one. So, you can only choose those labelings where these two values are the same essentially. Rishabh has a doubt.
I don't understand it, the arrow thing.
What arrow thing?
I understood what the convex and concave plus and minus sign meant, but the arrows I did not
See,
understand.
if I am looking at this device and I am seeing this edge, okay, I cannot see what's on the other side,
Yeah.
correct? So, an arrow edge is on the boundary of the object, that is the first thing. Then should I label it that way or should I label it this way? The convention says that the material is on the right side of the arrow. So, if my arrow is going that way, the material is here. If it was a convex, if it was this one for example, I would label it like this, because the material is on the right side. As you are going down the arrow,
Yeah.
material is on the right side.
Yes.
That is the convention of an
That's
arrow.
why I will label it.
So, an arrow, see an edge is between two faces, correct?
Yeah.
If you can see both the faces in the diagram, then you will label it as plus or minus.
Yes.
If you can see only one of the faces, then you will have to label it with an arrow.
Okay.
The question is, which side should the arrow point?
Yeah.
You point it in such a direction that the face you can see is on the right side as you travel along the arrow.